So here we'll look at a couple of more different interval of convergence problems, and then eventually we'll get into the endpoints of the intervals of convergence. I want to do this one just because we've been dealing a lot with integers so far, and I want to sort of point out that it is possible to work with values that are not integers. So suppose I look at this series, 3 to the n, x plus 2 to the n, over n plus 5. And I would like to find the interval of convergence. All right, so we start with the ratio test. We take the n plus first term divided by the nth term. So I'm going to take the limit as n approaches infinity of 3 to the n plus 1, x plus 2 to the n plus 1. On the bottom, n plus 1 plus 5 is n plus 6. Now, remember the old trick, we're going to multiply by the reciprocal. Instead of dividing by that original function, we'll multiply by the reciprocal. So I got an n plus 5. I got a 3 to the n, x plus 2 to the n. All right, let's try to arrange this in some semblance of order. I've got my 3's, so I got a 3 to the n plus 1 and a 3 to the n. Here I got an n plus 5 on the top and an n plus 6 on the bottom. And then how about the x's? I've got an x plus 2 to the n plus first. I've got an x plus 2 to the n. All right. So over here, 3 to the n plus 1 over 3 to the n is just 3. If I apply that limit as n approaches infinity to this middle piece here, that's just going to give me 1. Right? If you don't believe it, L'Hopital it, you'll end up with a 1 over 1. And this last piece over here is just going to yield an x plus 2, because there's n plus 1 of them on the top, there's n of them on the bottom, therefore x plus 2. Okay. All that is less than 1. So what do I end up with? I end up with the absolute value of 3 times x plus 2 less than or equal to 1. If you want, why not take that 3 that was on the inside there and move it on the outside, right? 3 is a positive value. And now I can divide both sides by 3, and I get the absolute value of x plus 2 is less than 1/3. Now, when I go to set this up with the absolute values, I'm going to have to put a negative 1/3 on the left side. X plus 2 goes in the middle. Positive 1/3 on the right side. Now, how do we solve this? Subtract a 2 from everything. Subtract a 2, subtract a 2. Negative 1/3 minus 2, well, negative 2 is negative 6/3. Minus 1/3 is negative 7/3. The middle piece is just x. And if I do 1/3 minus 6/3, I end up with negative 5/3. So this thing has a very small interval of convergence. The interval of convergence goes from negative 2 1/3 to negative 1 2/3, which means that my radius of convergence is only 1/3, right? The center of this particular series must be negative 2, which we can kind of see, right? You got an x plus 2. So the interval of convergence goes from negative 7/3 to negative 5/3. Is not very big. All right, let's take a look at another type of problem. Suppose I were to look at the series from k equals 0 to infinity of e to the kx. And I'm looking for information about how this thing converges. Well, what is this series? It's e to the 0 power plus e to the 1 times x plus e to the 2 times x plus e to the 3 times x and so forth. Isn't this the same thing as 1 plus e to the x plus e to the x squared plus e to the x cubed and so forth? This is really just a geometric series. Except my ratio here is e to the x. Well, if the geometric series converges to a over 1 minus r, and I know that e to the x converges everywhere, then can I just say that the sum of this series, or what it converges to, is a over 1 minus r? And so this 1 plus e to the x plus e to the 2x plus e to the 3x is really a Taylor polynomial representation for 1 over 1 minus e to the x. All right, the moment we've all been waiting for. endpoints of a geometric series. Actually, I should say endpoints of a Taylor polynomial, not in geometric series. So testing endpoints. Suppose I've got this series, and it's the sum from n equals 0 to infinity of -1 to the n, x minus 2 to the n, over n plus 1. And I would like to determine the interval of convergence, including the endpoints this time. All right, last few times we sort of ignored the endpoints. This time I want to include the endpoints. So this process for including the endpoints starts the same way as the other ones. Start with the ratio test. So let's take the limit as n approaches infinity, absolute value of -1 to the n plus 1, x minus 2 to the n plus 1. Down the bottom, n plus 1 is n plus 2. Let's multiply by the reciprocal of the original function. So I get a -1 to the n, x minus 2 to the n, and I want that to be less than 1. All right, so what does this look like when I move things around? You realize that -1 doesn't really matter in the end. -1 to the n plus 1 over here, and -1 to the n over there just becomes a -1, and the absolute value of -1 is just 1, so I'm good with that. All right, how about the n plus 1, n plus 2? I got an n plus 1 on the top, n plus 2 on the bottom, and then the other terms are x minus 2 to the n plus 1, x minus 2 to the n. All right, well, this guy over here, just like the last few times we did this, that limit just goes to 1. It's the same value top and bottom. And what I'm left with is the absolute value of x minus 2 is less than 1. All right, so my second step. Let's test the interval without the endpoints. So I will take my answer and I'll say -1 is less than x minus 2 is less than +1, right? Because if the absolute value is less than 1, that means that x minus 2 is between -1 and +1. I add 2 to everything, and I get 1 is less than x is less than 3. All right, and that's where we've stopped in the past, right? We said we're going to stop here, and we'll worry about the intervals of convergence, the endpoints later. All right, so now we need to test the endpoints. And the way that we test the endpoints is by taking each endpoint and throwing them back into the original series to create two new series. Okay, so the original series was a -1 to the n, x minus 2 to the n, over n plus 1. Okay, so the first thing we'll do is we'll work on x equals 1. Now remember, these are x's, these are not n's. So I'm going to come up with a series of -1 to the n, 1 minus 2 to the n, over n plus 1. Just to save some screen space, I'm going to do the 3 over here, and then we'll work down both ends. So I get a -1 to the n over here. I replace that x with a 3. So I get 3 minus 2 to the n over n plus 1. All right, simplify this a little bit. 1 minus 2 to the n is going to be another -1 to the n, so you'll have a -1 to the n. Then you'll have another -1 to the n. That just gives me 1. So this first series becomes the sum of 1 over n plus 1. This guy over here becomes a -1 to the n, but 3 minus 2 is 1. So when I multiply these together, I'm always going to get a -1 on top. Okay, so that second series becomes the sum of all the -1 over n plus 1, and really that should be -1 to the n. Great. So now we've got two new series. Test the convergence of each of those series. Here I'm not going to explain every little detail. Like this guy over here is really a harmonic series. I know the harmonic series is technically 1 over n, but if I add 1 to the bottom, it's not going to change this convergence. So we know the harmonic series diverges. Okay, so the series created by the left endpoint diverges. How about on the right-hand side? This one over here is an alternating harmonic series. Right, so what do we know about alternating harmonic series? We know that the alternating part converges because every term is greater than the term before it and the limit of the nth term goes to 0. So the alternating harmonic series converges. So the rule is if it diverges, don't include it. So if it diverges, don't include that endpoint. If it converges, include the endpoint. So my answer will be don't include the 1, but do include the 3. Now, the other type of question that you might see is, how does it converge at its right endpoint? So in this case, it converges, but how does it converge? Does it converge absolutely or does it converge conditionally? Well, in this case, we already have that test set up because it converges by the alternating harmonic series, but go back to that series over there, and it diverges. So at this endpoint here, it converges conditionally. All right, so you will not always have to check that. Sometimes it'll say, if it converges at an endpoint, how does it converge, absolutely or conditionally? In that case, then you would check. If nobody asks you about how it converges at the endpoint, then this is your answer right here. It converges on the interval from 1 to 3. It does not include the 1. It does include the 3. All right, should we try another one of these? Let's try another one of these. Suppose I look at this series. I've got x minus 5 to the n over n squared plus 1. All right, starting at n equals 0 to infinity. And I would like to find out the interval of convergence and tell me something about the endpoints. So let's start with the ratio test. Let's look at the limit as n approaches infinity of x minus 5 to the n plus 1 over n plus 1 squared plus 1 times, and then we'll leave the n squared plus 1 now on the top, the x minus 5 to the n on the bottom. And remember, the goal is to force this limit to be less than 1. All right, so let's look at the x minus 5s and let's look at the n's. The n's on the top are an n squared plus 1. On the bottom, I could expand that, right? I'll end up with an n squared plus 2n plus 2. And then over here, I end up with an x minus 5 to the n plus 1. And on the bottom, x minus 5 to the n. This first part over here, if I apply the limit as n approaches infinity, yeah, this is going to take me 2 steps if I want to actually go through the L'Hopital process. But if I do that, I'm still going to end up with a 1, which means that the only thing that's left then is that x minus 5. So the absolute value of x minus 5 is less than 1, right? That first piece, that limit goes to 1 because you've got n squared over n squared. The second piece, you've got 1 more x minus 5 on the top than you do on the bottom. All right, run that through the next line, and you end up with negative 1 is less than x minus 5 is less than positive 1. Add a 5 to everything, and you end up with an interval between 4 and 6. Now, the next thing I'd like to do is I'd like to test endpoints. So I'd like to test x equals 4, and I'd like to test x equals 6. All right, the original series had an x minus 5 to the n, so that x is 4, so I get 4 minus 5 to the n. And on the bottom, we had an n squared plus 1? Yes. Right over here, if you put in a 6, you'll get 6 minus 5 to the n over n squared plus 1. Well, 4 minus 5 is negative 1. Negative 1 to the n over n squared plus 1. 6 minus 5 is 1, so I get 1 over n squared plus 1. This guy over here is a convergent p-series, right? It's a p-series with p equal to 2. If you want, you can run through limit comparison tests and so forth to show that the two series are the same. But yes, 1 over n squared is a p-series, and it converges. On the other side, this is an alternating series, so this thing converges also. You can say it converges by the alternating series test. The terms go down, the limit goes to 0. What does that mean? Well, that means I end up including both endpoints. I include the 4 and I include the 6. If somebody asks me if it converges conditionally at either endpoint, the answer is no, because at this point over here, it converges absolutely. Because if you look at the two series, right, if I take out that negative 1 to the n, then I'm left with the series that's on the right. Well, if the 1 over n squared plus 1 converges, then the negative 1 to the n over n squared plus 1 converges absolutely. Okay, so this one does not have either endpoint where there is conditional convergence. There is absolute convergence at both endpoints. All right, we'll do one more part for this, and we'll do sort of a challenge problem, and then we'll wrap things up with a little bit of integration and derivatives.